In section 6.2 and 6.3, we're going to talk about properties of sets, how to disprove a property of sets, and more types of proofs for sets. We can find some of these properties through the use of intersections, unions, complements, and differences. And some of these properties will hold for all sets, some will hold only in certain cases, and some won't hold for any sets at all. It's our job to either prove or disprove that relationship. So before we can do that, we need essentially an order of operations for sets. The union, intersection, complement, and difference take preference over the subset. So I gave you an example here that said A intersection B subset C. And what that means is that A intersection B is a subset of C. I will often use parentheses to clear up any confusion. I don't like anything being vague about what we're trying to prove. So I may use more parentheses than your textbook does if you look at some of the textbook solutions. So before we can move forward in writing our proofs, we need to have some definitions for some of our properties, and we need to talk about some of those specific relations related to sets. So let's talk about subset relations. So for subsets, we have inclusion of intersection, which says for all sets A and B, A intersection B is a subset of A, and A intersection B is a subset of B. And that makes sense because the intersection of A and B is where they overlap, so they're in both A and B. So they would be a subset of both A and B. Inclusion in union says for all sets A and B, A is a subset of A union B. And this honestly could be A is a subset of A union any other set, because that means it's in A or any other set. And so automatically A is a subset of A. The same thing holds for B is a subset of A union B. Our transitive property says for all sets A, B, and C, if A is a subset of B and B is a subset of C, then A is a subset of C. So you might remember seeing this one, we talked about how we had the set of integers being a subset of rationals, which were a subset of the real numbers. So if the integers are a subset of the rationals and the rationals are a subset of the reals, it's quite obvious that the integers here are also a subset of the reals. And that's how the transitive property works. So our last bit of information on the first page are our if and only if definitions. So we're going to be using element argument proofs again, much like we did in the last section. And in this case, we're going to be letting A and B, and if we need it, C, be any sets. So instead of having them being defined on a specific set, now they're very general. So we need some more specific notation for what it means, and we're going to be doing operations on them. So we need some more specific information about what does it mean to be an intersection, what does it mean to be a union, etc. So if we let X and Y be subsets of our universal set U, and we suppose small x and small y are elements of the set U, then we say that X is an element of the union of sets X and Y if and only if X is an element of set X or X is an element of set Y. So X is in X or X is in Y. For X being in the intersection, that says that X is in X and X is also in Y. For our set difference, our X is an element of the set difference if and only if X is an element of set X and it is not an element of set Y. And our last definition says X is an element in the complement of set X if and only if X is not an element of X. We're going to be using all four of these definitions to help us write proofs for the remainder of this section. So what does an element argument proof look like with properties of sets? Let's look at one. For example, 6.2.1, A, I have that for all sets A and B, A intersection B is a subset of A. And we want to prove this. So our statement says, okay, well, for all sets A and B, A intersection B is a subset of A. So our proof is we're going to suppose A and B are any sets. From there, we need to show that A intersection B is a subset of A. So we're going to let X be an element in the leftmost expression. So X is going to be an element of A intersection B. And if you'll remember from our definition of subset from section 6.1, then our job is to show that X is also an element of set A. So we're going to say that X is an element in set A and B, right? A intersection B. So by the definition of intersection on the previous page, we know then that X is in A and X is in B. And in this case, in particular, we only needed to show that it was an A. Done, right? So we're just going to point out that we've already shown that. So we're going to say, in particular, X is an element in A. So thus, for all X in the set A intersection B, X is in A. Therefore, by the definition of subset, then we know that A intersection B is a subset of A. And that's it. Not too terribly complicated. Our next proof is also equally not that complicated. Let's see what 6.2.1b is asking us to prove. That one says for all sets A and B, A is a subset of A union B. So if you notice, this is our second property from the previous page that we're proving. So let's see here, our statement this time is that for all sets A and B, A is a subset of A union B. So our proof, we're going to suppose A and B are any sets. Then we're going to let X be an element of the leftmost set, which is A. Then, by the definition of union, we know then that X can be in A or X can be in any other set at all. In particular, let's choose set B, which we've already defined. So we know then, by the definition of union, X is in A or X is in B. So thus, X is in A union B. So it follows then, that for all X in A, X is also in A union B. Therefore, by the definition of subset, A is a subset of A union B. Now let's try our hand at a larger proof. We're going to prove the set difference law, which says for all sets A and B, A minus B is equal to A intersection B complement. So we're still going to have our statement where we're going to say for all sets A and B, we're claiming A minus B equals A intersection B complement. Our proof is going to start the same as all the others. Suppose A and B are any sets. So now, much like we had in section 4.5 with our cases for even and odd, we're going to have cases here, just like we did in section 6.1 when we had to prove different subset relations. So our first case is going to be where we need to show that A minus B is a subset of A intersection B complement. So here we're going to start by letting X be an element of the leftmost expression. Here, our leftmost property, A minus B. So X is going to be an element of the set A minus B. By the definition of set difference, what that means we can say about X then is that X is in A and X is not in B. Right? That's our set difference. We take A and remove from it anything that's in B. So from there, we can get closer to where we need to be by saying, let's use the complement then. Instead of saying X is not in B, let's make it X is in the complement of B. So by the definition of complement, we know X is in A and X is in B complement. So we have an and now. So by the definition, and means intersection. So by the definition of intersection, we now know that X is in A and B complement. So thus, for all X in the set A minus B, X is in the set A and B complement. Therefore, by the definition of subset, we can say then that A minus B is a subset of A and B complement. Case 1, done. Pretty straightforward, very similar to the last two proofs we did. And now we're going to do the same type of proof. We're just going to flip-flop the order. Now we're going to show that A intersection B complement is a subset of A minus B. So let's write that in here. So we want to show that A and B complement is a subset of A minus B. And this time we're going to let X be in the leftmost set again, which is going to be A and B complement. And you'll notice we're kind of just going to undo the process of what we did on the last one. So by the definition of intersection, right, by the definition of intersection, then we know that X is in A and X is in B complement. Well, we can say by the definition of complement, we know then that X is in A and X is not in B. Well, that's also the definition of set difference. So by the definition of set difference, we know then that X is in A minus B. So thus, for all X in A and B complement, A intersection B complement, X is in A minus B, the difference of A and B. So therefore, by the definition of subset, we can say then that A intersection B complement is a subset of A minus B. And much like in our previous examples with cases, we need a conclusion to wrap it all up. So we're going to say, by the definition of set equality, A minus B equals A intersection B complement, because, I suppose we can do B slash C, because both set containments have been proven. And that's it. What about sets that involve the null set? How could we write a proof about operations involving the null set? Well, we can still use the element argument method, but here to prove that a set X is equal to the null set, we need to prove that X has no elements. So to do this, we're going to suppose X does have an element and derive a contradiction. So an extension of section 4.7. So we're going to prove for any set A intersected with the null set is the null set. So our statement says for all sets A intersected with the null is equal to the null. So in order to do a proof by contradiction, we need the negation. The negation would be, well, flip the universal to an existential. There exists a set A such that A intersected with the null does not equal the null. So our proof is we're going to suppose there is a set A such that A intersected with null doesn't equal to the null set. What that means then is there exists some element X that is in the A and null set. So by the definition of intersection, we can say then that X is in A and X is in the null set. However, this is a contradiction. Right? This is a contradiction because the null set has no elements. Right? Thus, or therefore, for any set A intersected with the null is equal to the null. So not terribly involved. Literally just use the contradiction to try to claim that there's an element in the null set, and that violates the definition of the null set, and your contradiction is made. So what happens then if I were to give you a property that doesn't hold true for every element? That's when we have to learn how to write a disproof. how to disprove a set property. Let's look at example 6.3.1 to give us some guidance. Is the following property true? For all sets A, B, and C, the difference of A and B, union with the difference of B and C, is the same as the difference of A and C. So where we're going to have to start here is with our Venn diagrams for each side of the equality. So I've added in the Venn diagrams for A minus B union with B minus C and A minus C. Just from a visual inspection, we can see how different they are. We're missing all of this area in B that's not in C, and we're missing this area that is in A and C. So it's quite obvious that they are not equivalent. So this property is not true. So how will we go about disproving this? So we could, right, we could choose an element from either of those two regions. So we could choose an element from, let's see, that would be A intersection with B, or sorry, with C. A intersection with C minus B. So that is the intersection of A and C minus the B part. So it would just be this little bit here. We could choose one there because it's in the left-hand expression, but not the right. Or we could choose something that's out here in B that doesn't include A or C. So we could choose it from here or from B minus A minus C. We have a couple of options. On the next page, I'm going to walk you through how to assign different values to each of A, B, C, and the universal set. So we're going to build an A, a B, a C, and a universal set. And we're going to then show that there are elements that are in A intersection C minus B that are not in A minus C. So where do we even begin trying to write a formal disproof for this equation? Well, what happens here is we can use our Venns to help us formulate a counterexample. We, however, cannot, and I repeat, cannot use Venns as part of a proof or disproof. Venns are not a means of proof. They are a tool to help us see whether the property holds or does not. You will not be given credit if you include a Venn as your proof. If you include it as a means to decide whether you can prove or disprove it, absolutely great. I might even require it. However, you may not include it in your formal proof or formal disproof. It is not a method of proof. So now that we've got that out of the way, we're going to find our counterexample. So looking at our two Venns, we know we can formulate a counterexample by choosing an element from the area where A and C overlap, but B is not included. So let me get a little more space here and we'll bring that in and show that. All right, now we have our empty Venn. And where we're looking is this area right here. Right, my highlighter is not the best on this app. So it's that little area where A and C overlap, but B is not included. So the way that we can formulate our counterexample is we're going to choose an element from A intersected with B minus C as a counterexample. So you might ask, how can I find those elements? What do I call them? Well, what we're going to do is we're going to add integer values to every, I'm going to call them region, right? Or every space on the Venn. And that's going to build our sets for us. So let's call this 1, 2, 3. The area of interest for us is 4, 5, 6, 7, and 8. So what we're going to do now is we're going to look at the circle that is A, and that's going to define what our new A is, right? So now set A is the set of elements 1, 2, 4, and 5, because those are the elements contained within A's circle, right? 1, 2, 4, and 5. Likewise, B is going to be 2, 3, 5, and 6. So B is going to be 2, 3, 5, and 6. And hopefully by now you've figured out that C is set 4, 5, 6, 7. We don't need element 8 this time, but it's a good habit to include it in case you need it, in case you have a complement that you might need it. It's a set that's out, or it's an element that's outside of our set of 3 sets. So, where does our formal proof begin? Well, now that we can define all of our sets, this can help us find an example, because now we can use these sets to actually formulate the property trying to be proven, or in this case, we're going to disprove. So let's start with our formal disproof. So our formal disproof is going to still have a statement where we say, for all sets A, B, and C, we're claiming that A minus B union with B minus C is equal to the set A minus C. So now we're going to define our set. So in our proof, or in this case, disproof, we're going to define our counterexample. So we're going to let set A equal 1, 2, 4, 5. Set B equal 2, 3, 5, and 6. And set C equal 4, 5, 6, and 7. Then we know that A minus B is going to be the set 1, 2, 4, 5 minus any elements in the set that are also in the set 2, 3, 5, 6. And the elements they have in common are 2 and 5. So we're going to lose 2 and 5 and be left with the set 1, 4. We also know that B minus C is going to be 2, 3, 5, and 6, that set, minus C, which is 4, 5, 6, 7. The only elements they have in common are 5 and 6, so we'll remove 5 and 6 from B, and we'll be left with the set 2, 3. Now, We also can say then that thus A minus B unioned with B minus C is now 1, 4, that set union with the set 2, 3, which is now the set 1, 2, 3, 4. I don't think that's going to be A minus C, right? Because we're going to say, however, A minus C is going to look like 1, 2, 4, 5, that set, minus the set 4, 5, 6, 7. They have the 4 and 5 in common, so we're left with just the elements 1 and 2. So it follows that A minus B union with B minus C does not equal A minus C. And we are done. You can follow the same numbering pattern on any disproof, and we will do another one together in class. So in the last slide, I accidentally solved the problem that we were talking about before instead of the one that was literally on the page. So instead, let's look at here on the problem at hand. So again, while we cannot use our Venn to prove or disprove our statement, we can use it to help us formulate a counterexample for our disproof. So in this case, and I'm going to draw these by hand, they're probably not going to be very pretty, but I'm going to draw them. Let's look at our Venn. Here is A, B, and C. These are not going to be beautiful, but they'll work. And we're looking here to figure out what A union B minus C looks like. So let's start with B minus C. Well, that's everything that's in B that's not in C. So it's going to be up in here. And I want to union A with that. So I'm just going to add into that anything that is in A, which means I'm going to add in all of this. Right? Let me see here. I'm going to put it in a different color. I'm going to add in everything in A that is also included. So it looks like this. So then what we have to look at now is we also need to look at our Venn for the other side with our A, our B, and our C. And that one's going to look a little more complicated because now we have to find A union B, which is going to be both of these top two circles together. And we need to find A union C. That's going to be all of A and all of C. And we want to say, what is A union B minus A union C? So it's A union B, so it's everything in B that is still blue. So we're really looking at this section over here. Or if I were to hash mark it, we're looking at this section here. Whereas on the other side, A union B minus C is literally all of this. So we definitely don't have equal sides here. So what we need to do then is, one more time, just like we did before, we're going to construct our counterexamples in the same way. We've got our universal set on the outside. We have our A, our B, our C. And I just realized I'm going to have to make that a lot bigger so that we can actually see the numbers in it. So let's look here. Let's make it bigger. So we have A, we have B, and we have C, and we have our universal set. So there's A, B, and C. So let's number them like we did before. 1, 2, 3, 4, 5, 6, 7, and we'll throw an 8 out here into the universal set. So just like we did before, we're going to write up our disproof in a very, very similar fashion. We're going to say, all right, now we can construct our formal disproof. So our statement says that for all sets A, B, and C, we have A union B minus C is equal to A union B minus A union C. So for our proof, we're going to go about it in the same manner that we did before. We're going to say let A equal, well, what did we put in A there? 1, 2, 4, and 5, right? 1, 2, 4, and 5. We're going to let B be everything that's in the circle that represents B. So in this case, it would be 2, 3, 5, and 6, right? Everything that's in B is 2, 3, 5, and 6. And C is going to be everything that's in the circle that represents C, which would be 4, 5, 6, and 7. And so this one's actually going to require a little bit more computationally from us than the last proof did. Because then we know that B minus C is going to be 2, 3, 5, 6 minus 4, 5, 6, 7, which is going to give us, well, what's in 2, 3, 5, 6 that's also in 4, 5, 6, 7? That's 5 and 6. We're going to be left with 2, 3. And then we want to find, thus our A union with B minus C is going to be unioning 1, 2, 4, 5 with the 2, 3. So when we do that, the only element that we're really adding is the 3, because we already had a 2. So we get A union B minus C as 1, 2, 3, 4, 5. So then we need to say, however, when we start looking at the right-hand side, A union B is going to be 1, 2, 4, 5, unioned with 2, 3, 5, and 6, which is now 1, 2, 3, 4, 5, and 6. And A union C is going to be 1, 2, 4, 5, unioned with 4, 5, 6, and 7, which gives us 1, 2, 4, 5, 6, and 7. So when we go to find their difference, A union B minus A union C, we get 1, 2, 3, 4, 5, 6 minus 1, 2, 4, 5, 6, and 7. So what are we left with? Well, 1 is gone, 2 is gone, so we're left with 3. And let's see here, what else are we left with? Well, 4 is gone, 5 is gone, and 6 is gone. Wow, so we're really, well and truly, only left with the element 3. So it follows that A union B minus C does not equal A union B minus A union C. And we can call it a day on that. You'll notice that I included a handout called Set Identities for you. And these are all a list of set identities that were listed in section 6.2 that we're going to apply for yet another type of proof for sets, which is an algebraic proof. So algebraic proofs are pretty handy because you can rely on all of these set identities to help you write a much quicker proof for your sets. So let's look at what one of these algebraic proofs might look like. So we want to construct an algebraic proof for the following statement. For all sets A, B, and C, A intersection B union with C is equal to A union C intersection with B union C. So we're still going to have a statement. And our statement is going to say for all sets A, B, and C, A intersection B union C is equal to A union C intersected with B union C. And here's where the cool algebraic proof comes in, is we're going to suppose A, B, and C are any sets. And from there, then we're just going to employ a bunch of algebra with the reasoning off to the right. So what we're going to say is then A intersection B union with C can actually be rewritten as C unioned with the intersection of A and B. And this is by the commutative law for union. So the commutative law for, and I'm just going to write the U for union. That is rule number one, or not, I guess not rule, identity number one on the handout. From there, we can also say then that that is C union with A intersected with C union with B by the distributive law, which is law number three, right? Identity number three. From there, we can also now rewrite this as A union C intersectioned with B union C. And that is, again, by the commutative law for unions. And that's what we were trying to prove. So we would say, thus, A intersection B union with C is equal to A union C intersected with B union C. And that's it. These algebraic proofs are really, really nice. So I'd like for you to try the last one, pause and come back and see if you can do that one on your own. Well, hopefully you've tried this one on your own. Here we're trying to show that for all sets A and B, A union with B minus A is equal to A union B. So our statement says that for all sets A and B, A unioned with B minus A, the difference of B and A, is equal to A union B. And our algebraic proof says suppose A and B are any sets. Then here comes the algebraic proof. A union B minus A can be rewritten as A union B intersection A complement. There we go, A complement. And this is by the set difference law. Difference, I've got some, there we go, some set difference law, which is the last one. What is that? Number 12, by the set difference law. From there, we can say then that that is A union B intersected with A union A complement. And this is, again, our distributive law. So by the distributive law. From there, we can say then that we have A union B intersected with your universal set. And that is by the complement law for the universal set. And then we end up in the very end, thus, with A union B by the identity law for intersection. And thus, we have just shown that A union B minus A is equal to A union B, and we're done.